Hey, this is Will with the PSU Electrical and Computer Engineering Tutors, and today I'm going to be talking about the basics of Verilog. The whole purpose of this tutorial is to help acquaint students with the basics of Verilog. We are going to be doing very simple implementations in Verilog. So if you were looking for something a little more sophisticated, this tutorial is probably not for you. We're just basically going to describe the whole purpose of using Verilog, which is a hardware description language that we use to model digital circuits. We're going to be using the Verilog Extreme with Bug Hunter Pro. That's available on the Windows computers in the ECE labs. You can also access this software from home, which I recommend. That's what I'll be doing today in this tutorial. And the link at the bottom of the screen has more information on that. What we're going to be doing is we're going to be implementing and simulating a 1-bit full adder, and then we are going to expand that 1-bit full adder to a 2-bit full adder by instantiating the 1-bit full adder twice. How we're going to do this is we're going to implement the module for our 1-bit full adder first, and then we're going to design a test bench for it to verify that it works properly. And the test bench is just going to apply some stimulus to the module and then give us the output. And we're going to repeat this process for expanding the adder, and I'll go over the little nuances that we'll have to address when we do that. Now, there's some things to remember here, and that's that Verilog is just like a real circuit when it runs. Everything's going concurrently. And also, if you've done programming before, hardware description languages and programming languages are two completely different things. There are some similarities, but there's things about what we're going to do that are far different from just regular programming, so please keep that in mind. Now, I'm not actually going to go over the design of the 1-bit full adder, but we do have to briefly touch on everything just so it all makes sense. What you're looking at right now is the black box representation of the full adder. On the left side we have our inputs, and on the right side we have our outputs. The way that this is drawn here, you can see that A and B are 1-bit inputs, and CI, which stands for carry-in, is also a 1-bit input. So we have 3 1-bit inputs on the left side, and this module, FA, which stands for full adder, has 2 outputs. So these 3 1-bit outputs these 3 1-bit inputs go into the module, and the module does its magic and then outputs S, which is a 1-bit output, and then CO, which stands for carry out, which is another 1-bit output. Here we have the truth table for this module, and we need this in order to derive our Boolean expressions. We're going to use this truth table to compose K-maps. The K-maps, of course, we'll do circlings in. We'll see that in just a second in order to get our Boolean expressions. This is a very standard thing, and if you're an ECE 171 student, at this point you are familiar with this. The left side of this truth table is simply counting from 0 to 7 in binary. Since we have 3 inputs, we have 2 to the 3 possibilities, and we can represent 2 to the 3 minus 1 values. So we can represent from 0 to 7 is what I'm saying. And on the right side are the outcomes of the inputs on the left side. So this is very standard. The sum is just the result of adding A and B together, and the carryout is just whether or not the sum produced a carry bit. Here you see the K-map for the sum and the circlings that correspond to the Boolean function for sum, and there's some reduction here, some little Boolean algebra magic that is done in order to get a simplified expression that you see on the bottom of the screen. And this is the K-map for carryout. Same thing, circlings, and then a nice Boolean expression from those circlings. And so we just saw the Boolean expression for sum. This is the Boolean expression for carryout. These are the two Boolean functions for sum and carryout that we will be using in our implementation. Here is a circuit schematic for those Boolean expressions. And this is what we're going to build in Verilog. This is a visualization of it anyway. So as we're going through the implementation, keep this in mind, because this is the guts of that black box that we first looked at. And this is, what we're going to put into Verilog in order to get the desired behavior for the full adder. Okay, so what you're looking at right now is you are looking at my remote desktop, and yours might look a little different, but that's okay. The important thing is that you're going to go to the Start menu, and you're going to go to All Programs, and you're going to look for a folder called Synapticad. Once you're there, you're going to select Simulation plus Debug, and then you're going to choose Verilog Extreme plus Bug Hunter. It normally takes a second to pop up when you're using the remote desktop, but if you are in the lab doing this, you should boot right up. And there it goes. I'm going to make this window full screen. The simulation log was enlarged. I just minimized it or made it smaller. This is going to be important when we simulate, but for now it's not, so I'm going to minimize it. You're going to go to New Project, and you want your project directory to read like mine, N. You can type that in manually, or you can go to this button here to the right of project directory and click on it and then find it and select it. And you're going to want to give your project a name. I'm going to give my project the name Verilog Tutorial. And now there's this window here that shows all these folders associated with your project. User source files is going to be the most important folder for us, but right now this window is not important. We're going to go straight into implementing the 1-bit full adder in Verilog, and to do that we're going to go to the Editor menu and select New HDL file. And I'll make this bigger. We are going to do a structural description for our 1-bit full adder. I'm going to forego the behavioral because it's a lot easier to do the behavioral. All you're going to need for that are the Boolean equations, and it's really straightforward. It's some assignment statements. As opposed to the structural where you actually need to declare your gates and give them a propagation delay. So what we're going to do is we're going to declare our module with the keyword module, and I'm going to name mine full_adder. Don't use spaces because spaces are not allowed for variable and module names in Verilog. And I'm going to use the arguments. I'm going to use the same labels in the arguments of the module as we had in our truth table and K-map. And so I'm going to put a little comment here, and to do that I'm going to do / twice, and I'm going to say full_adder is the name of our
module, and A, B, CI, S, and CO are the arguments. Now I'm going to declare my inputs, and I'm going to do that with the keyword input. So from our black box we know that A, B, and CI are the inputs. And we know that our outputs, we're going to declare that with the keyword output, are S and CO. Notice how each one of these statements has been terminated with a semicolon. So that's an important thing to do, is that each statement that you have in Verilog, you need to terminate it with a semicolon. You will often run into compiler errors because of missing a semicolon. So that's something to keep in mind as we're going here and as you're following along. If you do everything that I do, it should compile and work just fine. If you miss a semicolon or a comma or something like that, you'll get a compiler error. Don't freak out, just examine the code, make sure it matches up with mine, and you'll figure it out. Next, since I'm doing a structural description, I'm going to need some wires, so I'm going to use the keyword wire. I'm going to have wire 1, wire 2, wire 3, and wire 4. I think that'll cover it for what we're doing. And so these are just wires to connect stuff. As I had mentioned earlier, doing simulations in Verilog is just like building a real circuit. So you're going to use these wires to connect circuit components, namely in our case the gates that we're getting ready to declare. So I'm going to refresh our memory here with our Boolean functions for the 1-bit full adder. So sum is equal to carry in XOR A XOR B, and carry out is equal to A and B, or A and carry in, or B and carry in. I'm going to do the XOR gates first, so I'm going to use the keyword XOR. And after that, I'm going to put a hashtag 2 or a pound 2, whatever you want to call it. And this is going to give us a propagation delay of 2 nanoseconds. And so we're going to do this for each one of our gates. The reason I'm doing that is because you will often do that if you're in ECE 171 for your projects. You'll often give your gates a propagation delay when you do a structural description. And of course we know in real life that gates have a propagation delay. The signal needs to go through. And so in order to get a realistic simulation in Verilog, we have the propagation delay. Now I'm going to give my gates the name for XOR. I'm going to use U0. For the first gate, U0A. And the first argument is always going to be the output. And so I'll use wire 1 to represent the output of this XOR gate that I am declaring right now. And the inputs to that will be A and CI, which is carry in. And I'm going to put a comma at the end of that because I'm not done declaring my XOR gates. So the next one is going to be U0B, B as in Bravo, and so I'm going to take the result of A XOR CI, which is carried in, and that result I'm going to feed in to this gate that I'm doing now, and the output of that result will be the sum. So my output is going to be S. And like I said, I'll be feeding in wire 1 as one of my inputs, and the other input will be B. And then I'm going to terminate with a semicolon. And that's because I'm done with my XOR gates. So now I'm going to do my AND gates. and they're going to have a prop delay of 2 nanoseconds as well. And I'm going to add some additional comments here. So this is A XOR CI goes to wire 1, and then wire 1 XOR B goes to sum, or S. And so we've got to start declaring our AND gates now, and we're going to do that for the carry out function, CO. So U1A, and the output of this one will use wire 2 for that. And A and B will be the inputs into the first one. So if you're looking at the functions just above these statements, I'm literally going from left to right. So A and B, comma, and then I'm going to do the A and carry in. And so for this gate I'll call it U1B, and I'll use wire 3 for that. So that's going to be A and carry in, comma, U1C. That'll be my last AND gate, and I'll use wire 4 for that. And that's going to be B and CI. And I'm going to terminate with a semicolon. And then I have to do a couple, actually I just do one OR gate. I can do a 3 input OR gate, so that's what I'll do here. So OR gate, again, prop, delay, 2 nanoseconds, U2A. Output will be carry out, and I will use wire 2, wire 3, and wire 4. And so those will all go in and they will get OR'd together, and the result of that will be carry out. And I'll put some additional notes here. So this is A and B. This is A and carry in, and so that goes to wire 2, goes to wire 3, and B and carry in goes to wire 4, and then so this is wire 2 or wire 3 or wire 4 goes to carry out. So we've very much just designed a circuit. I know it's kind of hard to believe because we just wrote a bunch of code. But basically in your brain, imagine the circuit schematic that we saw earlier, and that's exactly what we've implemented here in Verilog. So now that we're done, we're going to say end module because we're done. And that is the structural description for a 1-bit full adder. And so I'm going to save this now. I'll call it 1-bit capital FA for full adder. Save. Boom. Done. And so now we're going to move on to the test bench. So we're going to go to editor, and we are going to create a new HDL file. And so this is going to be the test bench for our full adder, our 1-bit full adder. And we're going to first start by declaring our module. Call it module test underscore 1-bit add, terminate with the semicolon. Notice how there's no arguments into this. It's not necessary. This is a test bench. This is not an actual device or anything that we're creating. So we're going to declare a register. Let's see. So we're going to have 3 inputs, and I'm going to, since those are all related signals, I'm going to declare them as a bus. So a 3-bit wide bus, and one of those bits is going to be the carry-in, and the other 2 bits will be the bits that I'm adding together. So this register A is my inputs. And then I'm going to have some wires for my outputs. So I'll have sum and carry out. And these will be my outputs. Now I am going to instantiate my full adder. And notice how I have a space in between full underscore adder and then a this FA. So let's do like some FA0. So that's my the name of the module that I've just instantiated, and you need to do that. You can't just have full adder and then your arguments. It's not going to work. You need to. You've basically brought the full adder into existence by instantiating it in Verilog, and so you need to give it a name. And so FA0 is the name of that instantiation. And so I'm going to do something here that most the time doesn't get covered, I think, in ECE 171, although it might be familiar to people who have taken ECE 351. I'm going to do my arguments by name. So there's two ways that you can feed your arguments to the module. You can do it in order, or you can do it by name. Actually, you know what? I think I'll do it by order first, and then I'll do it by name, just to show you the difference. So when you do it by order, that means that you need to feed in the correct arguments in the same order that they are done in your module declaration. So, for instance, let's say that the first bit of A is going to be the bit A for our full adder module. Okay, so that's represented with A and then bracket 0 closing bracket. Okay, so now that's bit A in the full adder is A0. And then bit B is going to be A bracket 1 closing bracket. So now the second bit of the register that I've declared for this is going to be B in the full adder module. And A bracket 2 will be the carry-in. And so now in my full adder module, that bit is going to be associated with carry-in. And then, of course, S will be the sum, and then CO will be the carry-out. So I'm going to put some notes here. And so I'm going to do, this is A. This is B. This is carry-in. And then the other two, I think, are pretty self-explanatory there. So I've done this because I'm assuming that if you're watching this, you're probably a beginner at Verilog, so I don't want to confuse you too much. But we've basically just taken this 3-bit wide bus, and a bus is just some related signals, and we've broken it apart. And we've made 2 of them the input bits that we're going to add together, and one of them the carry-in bit to the adder. And so what's going to happen is that A0 and A1 are going to be the bits that get added together, and A2 is going to be the carry-in. And now let me show you how to do it by name. So this is so arguments to module done by order, and so this is how to do it by name. And so I'm going to keep it commented out, full underscore adder, FA0, and so I would do something like dot A, and then parentheses A bracket 0. So that's, now I've told Verilog that argument A is going to be A0, which when I've done them in order and they correspond properly, the statement above this, right, the full adder FA0 that I just did, it's the same thing. But when you do it by name, it doesn't matter if they're in order or not. So let me clarify. So I can do something like this: B dot B, and then A1. And I'm gonna test both of these to prove to you that this works. And then dot CI here is going to be A2. And so order doesn't matter here. All right, I'll do CO first. And I believe that should be it. So we got A, we've got B, we've got carry in, we've got carry out, and we've got sum. Okay? So this is how to do it by name. And it's a, when you have, modules that have a lot of arguments, this doing it by name comes in handy. Notice how our module has 5 arguments, and that to me seems like a lot. Some people, may say you need more arguments before you would do it this way, but I personally always do it this way whenever I'm doing Verilog. I always do my arguments by name. I never do them by order because I never remember the order that I've declared them in. And, that helps free up memory space in my brain to remember something else, right? So I've instantiated my full adder here, and in this way, this first line, the line that my cursor is on right now, this is done by order. And so that's the one that we'll test first, and then I'll show you that you get the same result when you do it by name. And now we need to begin testing values. So we start with initial, and then we begin. And so we're going to do the, here, let me go back here. First set of inputs. 0. I'm doing 1 apostrophe B 0. That's binary. And the way that I'm about to do it is the way you're probably going to want to do it at first, because I'm assuming that whoever's looking at this is, a beginner in Verilog, or maybe you're just brushing up. That's fine too. But a lot of people, always in my experience, do not have programming backgrounds when they go into ECE 171, and then they get to the Verilog project and they don't know what a for loop is. They have no concept of how to do that, what it is. But that's how you're going to want to actually test your devices in Verilog. You want to be able to exhaustively test them by iterating through every single value. Right now what I'm getting ready to do is I'm getting ready to go through every single value for our 1-bit full adder, and I'm typing it in manually. This is, the way that at first is probably going to make a lot of sense to a beginner. But as you continue on and we expand, let's say, which we will do in this tutorial, you're going to go from 2 to the 3 possibilities, which is 8. So I'm getting ready to do 8 different sets of inputs, right? And if you're expanding to a 2-bit full adder, you're going to go from 2 to the 3 to 2 to the 5 possibilities. So then you're going to have to do 32 sets manually, painstakingly. That's not a good way of doing it. I'm going to show you how to do it with a for loop, but if you don't understand the for loop, you need to keep it simple. You need to do it this way, that's fine. It's just going to be very time consuming. So I highly recommend using for loops. And so we're going to hold those inputs for something like 10 nanoseconds. So here, let me put some comments. And this is all being done live, by the way, so I apologize that this doesn't flow very smoothly. I'm trying to talk to you and type it at the same time, and of course none of this has been rehearsed. This is just me doing this, so to help out students who have questions for Verilog. So you're getting ready to witness the magic firsthand. So we're going to hold these inputs that we have here. So remember, A0 represents A in our 1-bit full adder, A1 is B, and A2 is carry in. And so each one of them are 0 to begin with, just like we saw in our truth table. We're getting ready to count from 0 to 7 in binary. And so all we're going to do is I just copied, and I'm going to paste. Oops, you know what? I'm going to copy all 3 of them. Sorry. It'll be a little more efficient. I'm sure you'll agree with me on this. Copy all three. Boom. We're going to be counting from 0 to 7, right? So we're going to want to go, we're going to want to be at 1 now, right? So we've gone from 0 to 1. And then again, we're going to do the same thing. We're going to hold those for 10 nanoseconds, and then we're going to go to 2. And so I hope that you're seeing the pattern here. This is going to be monotonous and tedious and not very enjoyable in my opinion. But you will get to see what it's like to do it a lot more efficiently using a for loop. Oh, I haven't saved this yet. I'm going to go on ahead and save this as test full adder. I'm in the habit of when I code, I hit Control S as I'm doing it just to make sure that I'm saving it. And the first time you save, it's always going to ask you to specify a file name. So now we're going to be at 4. And then 5. Be at 6 now. Yep. And then our last one is going to be 7. So again, I've gone through and done 1, 2, 3, 4, 5, 6, 7, 8 sets of inputs. Not very efficient, but it's going to get the job done. So now we're going to finish up because we've tested all the possible inputs. So hold the last set of inputs just like every other set, then finish up. And so that end that I'm typing there corresponds to this begin, and then end module. Okay, so now I'm going to run this. Hopefully it works. You do that by clicking the play button, and it looks like, oh, look at that, no source file for compilation specified. Well, that was my bad. So I did all that coding, right? And so what I forgot to do is I forgot to add those to the source files. So I'm going to go to that window that we saw in the beginning with all those folders that are associated with your project. And I'm going to add those. So I'm going to add the test bench, and I'm going to add the 1-bit full adder. So now those user source files are in there, and I'm going to be able to build now, right? So let's try this again. I'm going to hit the play button one more time. And there we go. Now it's starting to compile. It's going to take a second. And once it's done, it's going to show us the results on the timing diagram that's behind the simulation log. And like I said earlier, the simulation log is important when you're actually simulating because you're going to get your error messages and whatnot here. So that's where you would look for that stuff. Looks like everything's going normally. This is what it looks like when everything goes successfully. Notice simulation has been built. Once the simulation goes through, it'll say simulation good. Okay, so simulation is good. I'm going to zoom in on my timing diagram a little bit. And so notice how it plots your register, and that corresponds to your inputs, right? and then your outputs, which are your sum and your carryout. And so right now this signal looks like it might be in hex or decimal. So like I said, we counted from 0 to 7 in binary, so that's what we should see, and we do. But just for the sake of education here, I'm going to change this signal, and I did that by right-clicking and hitting Edit, selected signal. And it is in hex right now, but I want it to be in binary. And so it's in binary now. And so now I can verify my results. So this little gray area that we see on the timing diagram is the time it's taking for the signal to propagate. And so it hasn't made it through just yet, so you know, nothing is happening here that we can really be any use to us. So that's why it's grayed out. And so remember that the first two bits are the bits that we're adding together, right? And the last bit is the carry in. And so 0 plus 0 should give us a sum of 0, and we shouldn't have a carry out. And we don't. And so let's look at another case that might be a little more interesting. We have 1 and 1 here, and we know that when you add 1 and 1 in binary, you get 0 with a carry bit. And so our sum is 0, and our carry out is 1. And you know, you can just go on and you know, verify that all these results are correct. And so you know, here we have 0, 0. The sum of 0, 0, and our carry in is 1 should give us a 1, and we don't have any carry out now. Let's go look at our last case here. So 1 and 1, the sum there is going to be 1, since we have a carry in of 1, right? And then we're going to have a carry bit. So then we have our sum of 1 and our carry out of 1. And so if we, you know, look back at the truth table, we should see that this corresponds with what we have on our truth table. And so this is good. This is exactly what we want. So now let me show you real quick that the by name gives us the same thing as by order. So we run that. And it's going to take a little bit. Mainly because I'm on the remote desktop, but it also takes time even when you're in the lab. Just have to wait patiently. Simulation built. And right now you can see in the background what was there before. It's not going to change. It should give us the exact same thing. If it does change, then I've done something wrong. But I guarantee you it's just going to be the exact same output. And there you go. So 1, 2, 3, 4, all the way to 7. And the corresponding output signals, sum, carry out. And so there's by order. Now let's do a test bench with a for loop. We're going to do a test bench on our 1-bit full adder using a for loop. So I'm going to go to the editor. I'm going to create a new hardware description language file, and a better way to do the test bench for a 1-bit full adder. And so module test 1-bit add I'm going to do the same thing with my, basically everything's going to be the same. As a matter of fact, everything except for the guts of the initial and begin there is going to be the same. So let me just copy this. I'm going to paste it over. And so what we're going to do here is we're going to do a for loop. So for loop. So for, oh, and I'm also going to declare a integer up here in my variables. So integer is our keyword there, and I'll call it loop counter, so it makes a little more sense. Counter for the for loop. So for loop underscore counter equals 0 until loop underscore counter is less than 8. Loop underscore counter equals loop underscore counter plus 1. And so basically what that means is we're going to go from 0 to 7, right? Because once loop counter becomes 8 or greater, then we are no longer going to want to execute, because we're going to be past values that we want to test, right? We only want to test from 0 to 7. And each time we go through the for loop, we're going to increment the counter once, and that's what the statements are from left to right. So we start at 0, we want to end at 7, and we want to increment by 1 each time. And after that, we're going to do a begin. What did we do for our, we did like 10, so let me just do 10 nanoseconds. And then A equals loop underscore counter. So we are setting the input value and holding for 10 nanoseconds. And then end. And then we are going to hold for another 10 nanoseconds, just like we've done before. We're going to finish up, and then that end corresponds to this begin. So notice how we had to do a begin and end in the for loop, and then end module. Notice how much more efficient that is, and I'll call it test full adder 2. So much more efficient to do than writing out every single combination. And so this is something that you're going to want to make use of in your Verilog projects, because you could end up having a Verilog project where you have 2 to the 8 maybe possibilities. You're not going to want to write 2 to the 8 possibilities in your test bench. It would take you an enormous amount of time, and it's so prone to mistakes. Just do a for loop. And so now I'm going to remove the old test bench, and I am going to put in the new test bench, and I'm going to run it. And really, we're going to see that it gives me the exact same output as the other test bench. Or it should anyway. Yep. So it's going to give me the exact same output. And so once we take a look at this output and verify that it's good, we're going to expand the 1-bit full adder, and we're going to make it a 2-bit full adder. We're going to build a test bench to test that. And that will conclude the tutorial once we do that. Uh-oh. Build unsuccessful. Failed to check out the license for Extreme Simulator, and that is a cat issue. That has happened to me before, and normally to address that I just exit and re-enter and it'll work. Sometimes it'll ask you for the license still, but you have no control over the licensing. That is something that the computer action team takes care of, and I'm kind of glad that you're getting to see some examples of compiler errors in this tutorial, so you can know what to do when it arises. And so like I said, whenever I see that compiler error, I just restart. If it asks you for the license when you restart, just again exit out. Maybe even go to a different computer if you have to, if you're like in the lab, or if you're using remote desktop, log out of the remote desktop and then come back in. And so we'll try it one more time. Hopefully it'll work. It didn't ask me for the licensing, which is a good sign. So I'm anticipating that this will work. And now we just have to wait. And it's going through. And the simulation is built. And we should see the exact same output that we've seen before. Oh, the loop counter, you will see that signal, and it will be a 32-bit signal because integers are 32 bits in Verilog. And notice, let's take a look at the signal just real quick. It's in hex, but if we convert it to binary, look at that. Yeah, I see all those zeros. 32 bits. Not really important. It should, yeah. So it goes up to 8. It goes from 0 to 8. Even though 8 never gets put in, 7 only gets put in. So again, the only difference between the last output that we saw from our other test bench and this test bench is just this bottom loop counter. I'm going to go on ahead and hide it because I don't want to see it. I don't have any need for it. So let's look at this here. So 0 and 0 gives us a sum of 0, and we have a carry out of 0. 1 and 1 gives us a sum of 0 and a carry out of 1. That's good. Let's see, 1 and 0 with a carry in of 1 is going to give us a sum of 0 with a carry out of 1. So, and then the last case, of course, 1 and 1 gives us a sum of, and then we have a carry in of 1 that gives us a sum of 1 with a carry out of 1. So, all good.